Welcome everyone. Today I will discuss scalar triple product. We have already discussed dot product of two vectors, cross product of two vectors, and basic concept of vectors. So, scalar triple product. Scalar triple product. So A is a vector and we know P cross C, this is also another vector. A is a vector and B cross C is another vector. So if we take dot product of A and B cross C, then this thing, this is vector, this is vector, this is dot. So dot product is scalar quantity. So this is scalar quantity. Scalar quantity. So this is called scalar triple product. So what is definition? The dot product of A and B cross C is a scalar quantity. Is a scalar quantity and is known as scalar triple product. So it is denoted by box A, B, C. This is third bracket. So box bracket, that is why it is also sometimes called box product. Therefore, box A, B, C, we can also take comma. So A dot B cross C. So this is definition. Now let A equals to A1I, A2J, A3K. B vector equals to B1I, B2J, B3K. And C vector equals to C1I, C2J, C3K. So we take in general A as this, B as this, and C as C1, C2, C3K. Now we know B cross C so we are discussing the basic results. So B cross C, we know this is IJK, B1, B2, B3, C1, C2, C3. So I into B2, C3 minus B3, C2 minus J into B1, C3 minus B3, C1 plus K into B1, C2 minus B2, C1. So this is B cross C. And if we take dot product with B cross C, so look, dot A and B cross C. This is B cross C and this is A. So I dot I is 1. So A1 into B2 C3, B3 C2 minus A2 into B1 C3, B3 C1 plus A3 into B1 C2, B2 C1. Now we are getting this result. So this is denoted by box ABC. So this result, it is not easy to remember. So we write in determinant form: A1, A2, A3, B1, B2, B3, C1, C2, C3. So you know how to expand determinant. So if we expand, then we get this one: A1 into B2, C3 minus this, minus A2 into B1, C3 plus A3 into this. So box ABC equals to determinant. That is A vector, components of A vector, components of B vector, and component of C vector. So this is basic result. So most important result, box ABC equals to this one. Now box ABC, what does it represent? So faces are, we know, cuboid. Faces are rectangle. Now for three-dimensional figure, if suppose this is A vector, this one is B vector, this one is C vector. So this is OA, this is OB, this is OC. Now this figure, this is origin. This figure, so if faces are rectangle and one face is perpendicular to other, then this one is called cuboid. But look at the book, this book. If we pressed it, look, these faces will become parallelogram and it is not perpendicular to this face. This type of figure is called parallelopiped. This is parallelopiped. This one, this figure, this is called parallelopiped. So rectangular parallelopiped, this is called cuboid. So this is parallelopiped. So its three coterminous edges are A, B, C. So box ABC, we are not proving it. Box ABC, what does it represent? Box ABC represents volume of parallelopiped whose coterminous edges. So look, they are from O, approaching, they are away from O, whose coterminous edges are A vector, B vector, and C vector. So this is geometrical representation also. What does box ABC represents? Box ABC represents volume of parallelopipe whose coterminous edges are A vector, B vector, and C vector. So you remember this one. Now note, this is most important result. A box ABC equals to 0. So volume equals to 0. So this three-dimensional figure will reduce to two-dimensional. That is, then A vector, B vector and C vector are coplanar. Coplanar. So coplanar. So box ABC represents volume of parallelepiped. This type of figure whose coterminous edges are ABC. If box ABC equals to 0, then vectors are coplanar. So to prove vectors are coplanar, we calculate scalar trivial product. If it is 0, then they are coplanar. Next, properties of scalar trivial product. Properties of scalar trivial product. Properties. Now number 1, box ABC equals to box BCA equals to box CAB. Box ABC equals to box BCA equals to box CAB. That is, value of scalar trivial product does not change if vectors are permuted in cyclic order. So look, A, B, C. This is cyclic order. So A, B, C, B, C, A. This is also in cyclic order equals to C, A, B. That is, value of scalar trivial product does not change if vectors are permuted in cyclic order. It is actually property of determinant. Look, box ABC equals to A1, B1, C1, A1, A2, A3, B1, B2, B3, C1, C2, C3. If we take A equals to A1I, A2j, A3k, B, B1I, B2j, B3k, C1I, C2j, C3k. Now, if we change first and second row, then B1, B2, B3, A1, A2, A3, C1, C2, C3. So, interchange of second row and this, we get minus sign. Now, if we interchange, so R2 to R3. Now, if we interchange again C2 and C3, then C1, C2, C3, A1, A2, A3. So, minus will be plus. So, R2 to R3. So, this is actually BCA. So, this is proof, very simple proof. Now, property 2. So, box ABC, this is A, this is B, this is C. Box ABC equals to box minus ACB equals to minus minus BAC. So if cyclic order is not maintained, we get same value, but we get a negative sign. Value of scalar triple product gets multiplied by minus 1 if vectors are not permuted in cyclic order. So exactly same proof, ABC, ACB. So interchange of third row and second row, you get negative sign. Now property 3. Three properties. Now we are discussing only for board problem. Basic concept. Now number 3. Value of scalar triple product. Scalar triple product. Value of scalar triple product is equal to 0 if any two vectors are identical or parallel. That is, box A, B equals to 0. Two vectors are same, so two rows or two columns are same, so value is 0. Also, lambda A, B or C as you please, this is also 0. A and B equals to lambda A, so they are parallel. So from property of determinant, if two rows or columns are proportional, then value is 0. So this is basic theory. So what is scalar triple product? What is its geometrical significance? And 3 properties. Now, 2 important results. So write box A plus B, B plus C, C plus A equals to twice of box A, B, C. And number 2, so for board problem, these are most important result, C minus A equals to 0. So box A plus B, B plus C, C plus A, twice of box A, B, C. If it is minus, then it is 0. So proof. Look, LHS equals to box A plus B, B plus C, C plus A. So this equals to, from definition, A plus B dot cross product of other two vectors. So if it is board's problem, and if it is not in terms of IJK, you have to use sequential step. So A plus B unchanged dot B cross C plus A, distributive cross product C cross A. Again dot product is, এখানে cross product is distributive. Cross product is distributive. Now, dot product is distributive. So, A dot B cross C plus B cross A plus C cross C plus C cross A plus B dot B cross C B cross A C cross C C cross A. So dot product is distributive. Dot product is distributive. Now this one is 0. This one is 0. Cross product of two same vector 0. Now look, again dot product, using dot product, A dot B cross C, A dot B cross A, A dot C cross A. Again distributive, B dot B cross C, B dot B cross A, B dot C cross A, B dot B cross C cross A. Dot product is distributive. Now from definition, this is box ABC. This is box ABA. This is box ACA. Box BBC. Box BBA. Box BCA. Now, from property we know, look, two vectors in box product are same. So these are 0. These are 0. So you write two vectors in box product are alike, therefore value is 0. So ABC plus BCA. Now you know box product remains unchanged if they are permuted in cyclic order. So BAC is again ABC. So twice of box ABC. So box ABC. So A plus B, B plus C, C plus A. Twice of box ABC. So this is important, most important property. Now this is your home task. If this one is negative, so this one is 0. Now may be given in twisted form. So look, alternative, if ABC, sometimes it is given in this form. If ABC are non-coplanar, then prove that A plus B, B plus C, C plus A are non-coplanar. Non-coplanar. ABC are non-coplanar. So they are equivalent result. So proof, you look, ABC are non-coplanar. Are non-coplanar. Coplanar. Therefore, box ABC scalar triple product is 0. Now we calculate box product of this one. A plus B, B plus C, C plus A. So we have already proved this equals to twice of box ABC. We have already proved it. Now this one is not equals to 0. So this is non-zero since box ABC not equals to 0. If box product is non-zero, then vectors are non-zero. Then vectors are non-coplanar. Proved. So this and these are equivalent. Now this is also you can state in alternative in theorem, in terms of theorem. Theorem 2, if ABC are non-coplanar, then prove that A minus B, B minus C and C minus A are coplanar. Then the vectors are coplanar. So look at the proof. Proof. A, B, C are non-coplanar. Therefore, box ABC, here for the previous one, this is not equals to 0. For the previous one, ABC are non-coplanar, box ABC not equals to 0. So A plus B, B plus C, C plus A, twice into this, not equals to 0. So the vector inside box product are non-coplanar. So this should be not equals to 0. Now for theorem 2, ABC are non-coplanar. Prove that A minus B, B minus C, C minus A are coplanar. So ABC are non-coplanar. Box ABC not equals to 0. Now we have to calculate A minus B, B minus C, C minus A. So this equals to, by theorem, this one, this is 0. This is your home task. So if box product is 0, then vectors are coplanar. Therefore, A minus B, B minus C, C minus A are coplanar. So these are equivalent result. Now for board problems, 4 problems. These 4 problems are sufficient. So 2 theorems and these 4 problems. So problem number 4. Find the volume of the parallelepiped whose edges are A, B and C. There are 2 marks problem whose edges are A vector, B vector and C vector. So volume of parallelepiped. So box ABC. So equals to determinant 2 minus 3, 4, 1, 2 minus 1, 2 minus 1, 2. So expanding we get 2 into 4 minus 1 plus 3 into 2 plus 3 plus 3 into 2 plus 2, 2 plus 2, 2 plus 2 plus 4 into minus 1 minus 4, minus 1 minus 4. So 6 plus 12, 6, 4 in minus 1, 3 into 2, 6. 4 into 3, 12, and this is minus 20. So minus 2. So what is volume? Volume equals to mod of minus 2 cube unit. Cube unit. So from geometrical significance, so box ABC equals to volume. Now problem number 1. The vectors these are coplanar. Find value of lambda. Now prove that the vectors this and these are coplanar. Prove that vectors are coplanar. And number 2, exactly same. These are coplanar. Find lambda. So consider problem number 1. So we find volume of the parallelepiped. So box ABC. 1 minus 2 3. Minus 2 3 minus 4. 1 minus 3 5. Now if we expand, we get 1 into 15 minus 14. 2 into minus 10 plus 4. Minus 10 plus 4. 3 into 6 minus 3. So this is 1. This is minus 12. This is 6 into 2, 12. And this one, 3. And 3, this is 9. This is 9. So 4, this is 6 into 2. So this is not 0. So let us verify the data. Vector I minus 2j plus 3k. So 1 minus 2, 3. So minus 2, 3 minus 4. 1 minus 3, 5. So look, this is 15 minus 12. This is 12. 15 minus 12. So this is 3. This one is 3. So value is 0. So box ABC equals to 0. So they are coplanar. They are coplanar. And for the third one, so I am giving hint. Look, 4 points are given. A, B, C, D. 4 points. So we calculate with AB, AC and AD. From 4 points, we can form 3 vectors. Now we prove AB, AC, AD equals to 0. And if we write this relation, then we get value of lambda. Value of lambda. So these problems are sufficient for both. So thank you for today.